Welcome back to AP Bio Walkthroughs with Jen. This is the second part of our chi-square video pair. That rhymes, pretty cool. Check out the chi-square basics, why to do it, what it is, and how to do it. Check out that video. If you are ready to practice, stay tuned because here we go. All right, guys, today we are doing a problem from one of the drills. This is chapter 12 drill, question 7 from this book, AP Biology exam with a butterfly on it for 2020. Okay, so if you got that, break it open, turn to page 285, number 7. If not, just follow along. Here we go. A mating is set up between two pure breeding strains of plants. One parent has long leaves and long shoots. The other parent has short leaves and stubby shoots. F1 plants are collected and all have long leaves and long shoots. So before we go any farther, what they are telling us is that they have bred two plants. One's got long leaves like this and long shoots. The other has short leaves and short shoots. They cross them and all of the F1 plants all have long leaves and long shoots. Okay, what does this tell us? That this particular plant with the long leaves and long shoots is probably dominant, right? Long. So we don't know if it looks like this or if it looks like this. But when we cross it with this guy down here, we get all long leaves and long shoots. Okay. Then those plants are self-crossed. So now we have another generation, and 1,000 second generation plants are phenotyped. And this is the data. And look what's happening. We're not just getting all long leaves and all long shoots like that first generation F1 plants. We're getting a lot of stuff. So we have 4 different phenotypes here. That means that this F1 generation that had all long leaves and long shoots probably did not look like this, okay? It probably was heterozygous. In fact, what probably happened is that when we took 2 of those F1 plants and crossed them together, what we were doing is making a dihybrid cross. Okay, so we know that all of these guys down here are results of a dihybrid cross. And if we think back to what we remember about dihybrid crosses, they have a ratio of phenotypes. It's called the phenotypic ratio. Okay, for dihybrid crosses, it looks like this. So this phenotypic ratio for the dihybrid cross is telling us what the plants look like, not necessarily what their genotypes are. Okay, so what this says is that 9 of them will have the dominant phenotype. Okay, so in this case, it's going to look like this. Long leaves, long shoots. Well, that's going to look like that. So unlike the AP Bio example, where we had an expected ratio or the dye sample of 1 to 1 to 1 to 1, our expected ratio for a dihybrid cross is 9 to 3 to 3 to 1. So we sorted out that this is a dihybrid cross. We're looking at a ratio of 9 to 3 to 3 to 1 right here in this table. Let's continue on and check out the question. Okay, so it says, are the genes for leaf and shoot length segregating independently? So I think it's important to mention that the law of independent segregation states that alleles sort independently of one another. Now, this is often violated, as we see now in modern genetics. With our modern technology, we can see this. But back in Mendel's day, he found this 9:3:3:1 phenotypic ratio is what you get if you've got 2 independent alleles. So when the question asks us down here, are the genes for leaf and shoot length segregating independently, we should be automatically thinking of phenotypic ratio of the dihybrid cross. Okay, so far we've just been talking about phenotypic ratio and leaves and shoots. How in the world do we know to use chi-analysis or not? Okay, here's things to look out for that will clue you in. So first of all, the way that I asked you the question can be answered in a yes or no answer. Okay, so you're probably going to be accepting or rejecting a null hypothesis. Your null hypothesis, as we'll see in a bit, is actually built right off your question. Second one is that you have degrees of freedom mentioned in every single one of these. All right. That's number 2. And number 3, look right there. You've got chi-square value in your options. So those are the 3 clues that should tip you off that, hey, you're going to be using chi-square analysis, even though it didn't say it at all anywhere up here, right? It's not mentioned once. So now that we know we're going to be using chi-square analysis, what do we do first? Well, we have to find our expected and observed data. Good thing is we already know what our expected ratio is. So we can actually calculate our expected data based on this ratio. Here's how we do it. Okay, so we know a few things. We know that our 9:3 to 3:1 is our expected ratio for that dihybrid cross. We also know that we have 1,000 total F2 plants. Something else we know is that 9 plus 3 plus 3 plus 1 equals 16. 9 over 16 would give our percentage. To find this percentage out of 1,000, you just set it equal to x over 1,000. Another way to do this, so you don't have to worry about cross multiplying, is to just say times 1,000 equals what? I got 562.5. Back here on my problem, I can plug that number in for my first expected value at that 9 ratio. If I do the same for the others, these are the values that I get, and they all sum to be 1,000. Okay, so at this point, it is really tempting to say, all right, I've got my observed, I've got my expected, I can plug those in to my chi-square formula and get my chi-square, degree of freedom table, find my critical value, compare it, and reject or accept my null hypothesis. But you're getting ahead of yourself if you do that, because we don't even have a null hypothesis yet. We have to make one. Luckily for us, they pretty much already gave it to us in the question. Okay, all we have to do is transform that into a null hypothesis, something like this. Null hypothesis are the genes for leaf and shoot length segregating independently, and then I threw that ratio in there to remind us that it needs to look something like this. Okay, so at this point we have our expected and observed values. We have our null hypothesis. We can do a little bit of plug and chug with that chi-square formula. But before we go and do all that work, let's look at the answers and see if there's anything we can already eliminate. So just looking at this, we can see that 2 of the answers have a degree of freedom of 3 and 2 of them have the degree of freedom as 1. What's our degree of freedom again? Remember from our first explainer video, our degree of freedom is n minus 1, with n being all the possible types or sorts or groups. In this case, it's all the possible phenotypes. How many do we have in our table? Let's see, 1, 2, 3, 4. Okay, so n minus 1 equals 4 minus 1. So our degree of freedom equals 3. Hey, what do you know? So automatically we can come down here and eliminate 2 of the answers. All right, so it's time to take our observed and expected values and plug them into our chi-square formula. So for this first value, you plug in 562.5 minus the observed, which is 382. Okay, you square that, and then you divide it by that. And this all comes out to 57.9. All right, then you're going to take this, put it over here, because you are going to add it up with all the others when you get done calculating them. Okay, so I've done this one. What's next? Plug this one in. So we have our expected at 187.5. You can go ahead and our observed at 109. And that equals 32.8. All right, do the same with these others yourself. And you get these values, then you are going to add them all up and they sum to this number right here. which is chi-square. So we've got our chi-square, we have our degree of freedom. The next step is to look at a table, find the column for our degrees of freedom, find the p-value that we'll be looking for, which is most likely p equals 0.05, because this is the value we work with a lot in biology. Unless they ask you to find 0.01, you are usually going to be looking at this value. So where's our table? Fret not, if you can find the formula sheet, you can find the chi-square table. Let's look for it. Hey, look, we found it. It is on our AP Biology equations and formulas sheet. And look what else is there. Our chi-square formula, how to find the degrees of freedom. We've got all the parts actually of our chi-square formula there. Very nice. But most importantly, we've got our table, which is right here. Okay, so find your degree of freedom. What was it? 3. That's right. Find your p-value. Which one are we going to use? 0.05. Find where they intersect. Bam, 7.81. That is our critical value. All we have to do is compare that critical value with our chi-square value and see which one's bigger. Let's go back. All right, so here we are comparing our values. If we look again at what our rules are, if chi-squared is less than the critical value, then we can accept the null hypothesis. If chi-square is greater than the critical value, then we must reject the null hypothesis. And what is it in this case? Which one's bigger? Is chi-square. And so we have to reject the null hypothesis. And what does that mean for our question? Just a reminder that C and D are out because the degree of freedom is 3, not 1. And if you remember what our null hypothesis was, then we can answer yes or no to the question, right? So are the genes for leaf and shoot length segregated independently? Well, we had to reject our null hypothesis, right? So that means yes is out because yes would be accepting the null. So our answer is B. No, the degrees of freedom are 3 and the calculated chi-square value is large. So go out, find your own chi-square analysis problems, practice them, comment below if you run into anything weird, comment below for any questions or any more videos you'd like me to do in the next 4 to 5 days. All right, adios amigos. Ahem.